So good morning, welcome to SUSECON. Just checking, everybody's in the right room. Good start. Right, so my name's Stephen Mogg. I'm one of the technical strategists in EMEA, looking after most things SAP and public cloud. And we're lucky enough to have Mark Gonnelly with us, who's one of our senior consultants. If you want a bit of clarification on those particular roles, Mark is the guy that does stuff. He's in data centers week in, week out, actually delivering tangible projects to customers. I tend to go around talking about things most of the time, so without actually necessarily delivering anything. So with those roles aside, what we plan to take you through over the next 45 minutes or so is just a quick look at some HA concepts. We'll take a look at SUSE's clustering solution, how we implement that technology inside Azure. We'll have a quick peek at best practices, or rather we'll be covering those as we go along. And if there's time at the end, we'll just show you it in action. So where to start? I don't think you can go to any session which talks about availability without covering off a few terms just to make sure we're all on the same page. So if you imagine this scenario here where you have a failure and then you recover the situation, and then at some point you have a failure in the future again. We have MTTF, or mean time to failure, is the time taken between failures. That's how long can you keep that service available. You have the pink box here, which is mean time to recovery. That is a case of, okay, so at some point things fail. That's kind of what happens in life. How quickly can you recover those services? All right. And at the bottom we have an RPO, or recovery point objective, and that is how far back in your business do you want to go to restore that to restore that solution. So, for example, a lot of companies want the smallest recovery point as possible. They want pretty much no difference between the data they restore or the data they recover and where the system failed. Other businesses, you may want to go back a day in time because it makes more sense just to recover to midnight and then re-input the day's work. It's normally a business decision, but most of the stuff that we cover, we try and shorten the RPO as much as possible as well. So when we talk about HA and high availability, we are talking about reducing the mean time to recovery. How quickly can we get those services back up and running? So one part of the solution is using the platform. Oh, picture. Thank you. So one thing, did I ruin that for you? No. So one thing we can do is use the Azure platform itself. Now, I'm not here to explain what Azure is. There's a booth downstairs and a number of other sessions you can go to. But out of the people here, who's using Azure? Okay. Who's using it for something really important? Good. And who's wrapped something around that to help protect that service, whether it be a cluster or some kind of HA solution? Okay, so I'm talking to you then today. Yeah. Okay. That's okay. So Azure's built up of hundreds of services. I don't think there's a month that goes by where I don't get an Azure newsletter in my box, which introduces a couple of extra services as well. But what we're talking about today is just a few boxes. We're talking about the compute, a little bit of compute, a little bit of networking, a little bit of storage. Because what we're talking about is perhaps bringing those traditional workloads into Azure, and that needs perhaps a different kind of approach to some of the cloud-native applications you might develop today. So let's talk about the actual platform, the Azure platform itself. So you can use something called HA sets in Azure. So what we're talking here is we're talking potentially two parts of the data center. They're on, or the racks that the VMs are on, two VMs in different racks on different power, different networks. And the idea is they will survive a power outage of the rack, a power outage perhaps of that corner of the data center, or maybe a maintenance event. The idea is that when something's happening to one VM, at least one of those virtual machines will survive somewhere else in that data center. The next thing you have is availability zones, and these have been introduced over the last couple of years. And again, I'm not here to tell you too much about Microsoft technology. I do recommend you visit the booth today. But what we're doing here is just increasing the size of that fault domain. We are, rather than protecting a rack or a corner of a data center, we're actually starting to provide protection on a much greater level. Oh, sorry, Microsoft done. The idea is that you have an availability zone, which is usually at least one data center, possibly more data centers. That becomes a zone, and then you're provided with two other availability zones in a region. The idea that if you have an outage on a much greater scale, like a a whole data center fails for power or gets flooded or something like that, again, a virtual machine running in a different AZ will survive that slightly more catastrophic event. One thing to point out is, and something we've kind of run into at one customer at least, was when you get your AZs delivered as part of your subscription, you get assigned 3 sort of random data centers to provide your 3 availability zones. If you get a second subscription, you'll get 3 other data centers potentially form those availability zones. So whilst in here we have availability zone 1, 2, and 3, if you're referring to availability zone 2 with this subscription and availability zone 3 with the second subscription, they have the potential to be the same data center. So if you want to look at balancing risk, you need to make sure that when you're delivering something in production, you do everything kind of under the same subscription, or at least be aware of the actual physical locations of your availability zones. So Microsoft actually does publish some SLAs, and these are widely publicized, but just for your benefits for today. The single VM SLA is 99.9%, which isn't bad. You put that in an HA set, so you protect that. You have 2 VMs in different corners of the data center. That increases to 99.95. And with the availability zones, where again that fault domain increases, one of those VMs will be available 99.99% of the time, which isn't bad. But if your business needs more, if you need to survive an outage in a slightly more agile way, then you need something else on top of that. So what we're going to do now is talk about the HA extension with SUSE.
Thank you, Stephen. So as Stephen said, my name is Mark Onley. I'm a consultant with SUSE Consulting based in Ireland. And I specialize in high availability. Generally speaking, today that means I do a lot of work with SAP because that's what we do, but I'm not really an SAP guru by any means. I'm HA, that's my background. So this is our HA stack. Now, if you look in our documentation, you'll find very complex diagrams with lots of moving parts. There's really only 2, right? And the 2 are a piece called Corosync, which is the cluster membership communication layer. It's the piece that the nodes use to talk to each other. They say, are you still there? When in fact, what they're actually, it's not a question. What they're actually saying is, I am still here. I'm still here. I'm still here. I'm still here. And then there's a piece called Pacemaker, which is the resource manager. Pacemaker is the piece that does the work. It's a start the application, stop the application, migrate it. It's what you think of as the cluster. And it's what you interact with. But in fact, really, the cluster, the talking to each other, is happening at this level. Now, above that, there's 2 other components in this diagram that are important to know about. Pacemaker doesn't understand SAP. It doesn't understand file systems. It doesn't understand IP addresses. It doesn't understand Apache. It doesn't understand any of the things it manages. Right? Instead, Pacemaker implements a set of simple operations: start, stop, migrate. Now, if I tell you, or Pacemaker tells a machine to, oh, I'd like you to start that file system. What does that actually mean in terms of a file system? How do you start in inverted commas, a file system? You mount it, right. How do you start an IP address? Yeah, you bind the IP address to an interface, right? So Pacemaker, like I said, doesn't know anything about that stuff. What Pacemaker does, it simply invokes a script that does the right thing for that resource. So there's a script to control file systems. There's a script to control IP addresses. There's a script to control SAP HANA. We ship about, I think it's on a later slide, there's about 140, 150 of them currently shipped by default with this. The point is that all the domain-specific intelligence, if you like, is in those scripts. And those scripts are called resource agents. Okay. Now, there's one other thing as well, something called fencing. I've got a few slides about that, so I'm going to come back to that, but it's very important, and in the context of Azure, we have something to say about this. So, okay, so Corosync, first of all, is the group communication system for implementing HA applications. It is the messaging and membership layer. It communicates over multicast or unicast. Okay. In Azure, we only do unicast. Now, on premises, people do both. Interestingly, when we shipped this in SLES 11 the first time, we only supported multicast because the actual membership protocol, it's something called Totem, is inherently a multicast protocol. So it's very easy to turn that into IP packets on the wire by doing a one-to-one Totem to IP multicast. Okay? And I would say on day one, the number one thing customers said to me was, when are you ever going to support unicast? Because doing multicast means you have to talk to the network people. And a little sort of chortle goes around the room. Fortunately, in the Azure world, that decision goes away. Azure, we're only supporting unicast in Azure. And this is, if you like, what we think of as the cluster heartbeat. Okay. Now, Azure is very simple because it's controlled by a single configuration file, etc corosync corosync.conf. And that file you just make identical on all the machines. And Corosync is typically set and forget. You know, when people say, oh, I have an interface to the cluster, I have a web interface or a command line interface, that's not Corosync they're talking about. That's typically Pacemaker. Okay, Corosync is typically set and forget. You create this file, and then you forget about it forever. Unless you have to grow your cluster, in which case you might have to come back. But typically, it's set and forget. And I'm going to talk a little bit about that later on. Okay, so Pacemaker sits on top of Corosync and monitors the cluster resources. It doesn't have a configuration file. It does and it doesn't. It represents the cluster, all the configuration, but all your resources, your SAP, your IP, your volumes, all that stuff, is represented in an XML file, and it's in the var file system. Don't worry about it. No user serviceable parts inside, as to say. It's not intended that the file should ever be edited directly. Instead, we provide you nice tools, a CRM shell and the Hawk web GUI to interact with it. Once Pacemaker is managing something in your cluster, then you really shouldn't touch the resource directly. In other words, if Pacemaker is mounting a file system, you shouldn't unmount it. Right? Because what will Pacemaker think? It thinks it's failed. It will try and restart it. And it will fight with you. And it will win. However, we do, of course, have in Pacemaker, there is a constant maintenance mode. Maintenance mode simply tells Pacemaker, hey, I'm going to do something manually. Don't freak out. And maintenance can be set globally on the cluster as a whole, on a node level, and on the individual resource level. So depending on what it is you're actually going to mess around with, you can set. Most people don't sort of set maintenance globally, which yeah, I don't know. Okay, so what it actually does though is it monitors those scripts. Remember I said those scripts, the resource agents? Resource agents typically implement a monitor operation. Because again, Pacemaker doesn't understand. If a file system is mounted, Pacemaker doesn't understand if it's unmounted, per se. Instead, the resource agent does. The resource agent has a function in it that checks, is that still mounted? And Pacemaker implements a monitor operation that simply invokes that script with the monitor parameter that causes the script to run and check is the thing still there. Now, so the resource agents provide intelligence to Pacemaker. They're scripts used to start and stop and monitor, and they should ideally be Open Cluster Framework, OCF. We provide, like I said, about 140 resource agents out of the box. resource ages for SAP HANA are included in the SLES for SAP applications. That's one of the big differentiators between SLES and SLES for SAP. The SAP instance arrays are in the standard SLES HA extension, but the SAP HANA arrays are only in SLES for SAP. I had a customer once ask me, well, does that mean I can just like run regular SLES and go to GitHub and download these things and run my HANA on regular SLES? And I said, well, technically yes, but in fact that's absolutely unsupported, not just by us, but by SAP. So if you want to run HANA unsupported by SAP, knock yourself out, and you will. Okay. So I mentioned fencing. I'm going to come back to this. I'm going to spend a little bit of time on this because this is important, and it's especially important in Azure. Well, it's equally important everywhere, but it has specific characteristics in Azure that we need to think about. Remember how I said the nodes talk to each other using Corosync? Now, imagine you have two nodes in a cluster, and they're talking to each other. And imagine they're physical nodes, actually physical machines. Right? And you walk up to one of them, and pull the power cable out of the back of the machine. So you know with absolute certainty that that machine is dead. Is it safe for the other node to take over its resources? For example, to mount a file system that was mounted. Is it safe? Yeah. We know it's safe. We pull the power cable. Now, wind back. Set the two nodes up again. This time you walk up to the machine, but you don't pull the power cable. You pull the network cable. Now, is it safe for the other guy to take the resource, to mount a file system, say? No, because the file system might be mounted over here. Okay. To a cluster node, the loss of a peer is indistinguishable from loss of communication with the peer. To a human, it may be obvious, but to the cluster nodes, it's not. And we need a way to distinguish, because in the former case, the loss of the peer, is it safe to fail the resources? This is a green light, yes. And in the latter case, no. So, if a node simply stops talking to us, we don't know, is he really dead or not? And that's where fencing comes in. When a cluster partitions due to a network failure, now this is not a node failure. This is the cluster partition due to network failure. Neither side knows if the other is alive. In the worst case scenario, each side would attempt to fail over the other's resources. That would be very bad. Right? A better scenario would be that neither side does anything. Hey, I was talking to that guy, and now I'm not talking to him anymore. I'm going to carry on doing my thing. But then why do you have a cluster? Why do you even need to know that he's dead? The best scenario is that one side is able to guarantee that the other side is down. And fencing is the term about moving from an unknown state. He stopped talking to me. Is he really dead? To a known state. Yes, he is. Now, we always fence. Go back to the scenario with the two machines. If I pull the power cable on this guy, remember that's indistinguishable to pulling the network cable. So in that case, the surviving nodes will always fence the other one. Even if it's already, because they don't know. They don't know what I know. Right? So they always fence. That's that's a common misunderstanding. People say, oh, my cluster's randomly fencing. And I'd say to him, how do you know that? Well, I scroll back in the log and I see a stoned action, a fence action. I said, did you scroll back further? Well, no, because that's what killed the node. No, the node may already have been dead further back, but he sends the fence anyway, just in case. Right? Okay. I was expecting one more slide there.
Can you talk about one other problem which I've seen in the past, not on SUSE, but race conditions? would there ever be a race condition issue here?
With fencing,
Yeah.
I am going to come back to fencing. We are in Corosync Azure, and I can answer that. It depends on the fencing method. So let's just park that for a moment.
Okay.
Yeah.
Okay, thanks. So that's our cluster solution. I'm giving you a 20-minute tour of a 3-day training course that's available. But essentially, we need to implement that technology inside Azure. So first thing is, it all depends on how you buy SUSE in Azure as to whether you get clustering or not. So there's 2 different ways to purchase SUSE. So either via the Azure Marketplace or via bring your own subscription. And we have 2 different offerings. We have our standard SLES server and also SLES for SAP. If you buy SLES for SAP, it doesn't matter where you buy it from. You get the HA extension included in that, so that's not a problem. If you buy if you buy SUSE Linux Enterprise Server via the Azure Marketplace, you have no ability to add anything onto that. You can't get the HA extension and provide protection to your applications. So you have to use our bring your own subscription model. And that's something just to bear in mind. If you do plan to provide HA capability to some applications, you need to think about how you're going to purchase it in the first place. But again, there's a public cloud booth downstairs that will tell you all about that as well. So when it comes to implementing some of this technology into the public cloud, it's the same. Pretty much you have the same conversation that Mark's just had, but we have to tweak a few things along the way. So we mentioned fencing, and one of the most popular fencing mechanisms that we have is something called SPD, which I'll let Mark cover off thoroughly, but it requires a shared block device. And you tend to find that public cloud providers just don't provide the ability for a raw block device to be shared between multiple VMs. So we need to rethink how we're going to deliver that. When it comes to shared storage, again, depending on your public cloud provider, you might get NFS, you might not get NFS. In Azure, I think there's an enterprise NFS service coming at some point, or at least the last time I chatted it was. But then there's also an SMB service as well, which provides local and geo-redundancy, which you could use for your file systems for these applications instead. And the last thing is, we have this thing called a cluster IP or a resource IP address, which is what your clients are going to connect into. And you'll need that to be available, but again, the way we implement it is different from an on-premise. And the other thing is, some of the cluster settings that you have, if you've been delivering Pacemaker on-premise for the last 10 years, ever since SUSE wrote it, you will find that when you translate some of that knowledge into Azure, things are a little bit different, okay? And one example is the Corosync changes.
Thank you. Remember what we said Corosync was? Corosync is the communication. Okay. Now, nodes are continually talking to each other saying, I'm still here, I'm still here, I'm still here. The interesting question that comes up is that if he stops, say for example the node has died, if he stops, how long do you wait? Because maybe the network's bobbled. How long do you, now it's actually quite complicated how it does this, but fundamentally there is one kind of master timeout setting, if you like, and it's this one. It's called the token timeout. And the token is expressed in milliseconds. Now, does anyone know what our default value for this is? I'll give you a clue, it's not 30. Does anyone know what if you just set up out of the box SLES HA and let Yaster or the cluster init tool generate a Corosync conf file? Does anyone know what it sets it to? It's 5. If you look in the default setting, you'll find that this is 5,000. And there's a related setting called consensus, which in the default is set to 6. Hence the rule of thumb, the consensus is 1.2 times the token. And that, now, actually before I go on, one other thing. Does anyone know, if you don't specify this, what the hard-coded value is? This is complete on this side. There's nothing to do with what we're talking about here. Just a little piece of trivia for you. I recently worked with a customer who was complaining about their cluster being wildly unstable. And when I looked in their Corosync conf file, there was no token line. So it was actually falling back to whatever the hard-coded value is, right? And it's 1 second, which is incredibly twitchy. Because of the way it works, it basically means your network can't bubble ever at all, which is not very highly available. So why 30? Well, if you take a look at some of the Microsoft documentation around clusters in Azure, not just our clusters, but even Microsoft clusters, you'll see that they set their watchdog timeouts and stuff to 30 seconds. When we first started doing this, HA on Azure, we were having problems with clusters being a little bit unstable, particularly overnight. And what we discovered was that Azure, it does background operations. For example, moving VMs around and making some network changes and stuff. And those changes take a little longer than 5 seconds sometimes. And so what was happening was the clusters were timing out. Now, remember what Stephen said about availability sets and availability zones. And of course, our sensible customers had placed their 2 nodes in separate, at least availability sets, in some cases in separate availability zones. So what would happen is, obviously, because the whole point is to have that redundancy, only one of them would do that. Only one of them would disappear for a little while. And of course, what that meant was that the other one, because it's in a different availability set, is not being maintained in the same window, would stay alive. And it would freak out because it would see the first guy disappear. Now, he would come back very quickly, but it was too late. Right. So we have implemented this as the recommended setting because it seems to cover all eventualities. Customers who've gone to this don't complain anymore about nasty things happening. Okay. You'll find, by the way, for all of this stuff, there is the official documentation from our friends in Microsoft. You'll find this setting documented there. So 30,000 for the token. Remember to get the right number of zeros. And 36,000 for the consensus. Right. And that's really only because the consensus is kind of tied to the token. Like I said, it's a little more complicated than just a simple timeout. Okay? That okay?
Yeah, thanks. Okay, so let's keep on the topic of fencing. So there are a number of different ways that we can elect to do fencing inside Azure. So the first one is to use what we call a service principal and the Azure Resource Manager fencing agent. All right. So again, remember the goal of fencing is to ensure that the other node is dead. And one way to do that is to use this. Now, the way it works is when it's time for the first node to fence the other, it actually won't, using this mechanism, it won't talk to that other node directly. What it does is it sends a request into the Azure framework and say, can you please go and shut down that other box? I need to make sure it's down before I can take over those resources. Now, as of today, the only way this can manifest itself is with a graceful shutdown, where the Azure framework says, can you go and shut down this box? Be as nice as possible. So it will try and unmount the file systems and shut down the applications and do all that sort of stuff before gracefully turning off and deallocating the box. Now, that's fine. However, you don't really know what state these boxes are in. It could be in any state. That's why fencing is kicked in. That's why you're trying to kill that other box. So what we found in practice over the last year or so is using this particular resource agent can take time, right? We're talking minutes, up to tens of minutes, just to make sure that other box is down. And until we get that acknowledgement back, this first node won't try and mount the file systems and restart those applications. Mm-hmm. So the concept of HA goes, you know, it's not that H at the end of the day.
Yeah.
It's,
Can I make a comment there, Steve?
Yeah, please.
One of the things Pacemaker does is when it opts to fence a node, there's a setting that controls the fence action. And the default fence action is restart. So in fact, it would require the service principal to stop the VM. And remember, the VM may be dead. It may not be responding at all because we fence in every case. It would have to stop the VM, deallocate it, reallocate it, and restart it before the resource agent would be, or the fencing agent would be told, hey, I've completely successfully fenced that node. So one of the things we found in our initial experiments was that you can shave a significant amount of time off it if you change the stoneit action to simply power off. Because then it simply shuts down and deallocates and returns that yes, I've successfully, which is enough. Okay. Of course, that means your VM now stays down. So there's a trade-off. There's you don't get something for nothing in this world. Even still, the shutdown and deallocate time can be quite long. So this is one of the situations where, how do we feel about this? It works great. It works perfectly. It just probably doesn't work fast enough for your HA requirements. Because after all, remember what Stephen said at the top of this presentation, the whole point of HA is to decrease the mean time to recovery. So we need to get that time down as low as we can. So the Defense Azure ARM agent, as documented here, does work, but probably not quick enough for you. It depends on what your needs are.
Thanks, Mark. So one thing I learned probably about 10 minutes before this presentation from some of the Microsoft guys at the back of the room is that there is potentially a new API call coming in the summer, which will just do a hard power off of a box. It won't try and gracefully shut it down. It won't try and be nice. It will just try and kill that VM. And once we get that, then this suddenly speeds up quite significantly. So that's something to look forward to. And that will, of course, it's just another resource agent which will integrate in, and we'll work together with Microsoft to make sure that works well. Did you want to cover off anything there?
No, this is just a typical representation of how the resource agent will be configured. Remember, as Stephen said, it uses an Azure service principal, which is effectively a username and password. So basically, you have to give it your login ID and password, and you get that from the Azure, the lovely Azure console. But the important thing is, as Stephen said, it does need that service principal to have the ability to turn off and turn on the machines. I've been with a couple of customers where by default, the people doing the Linux admin didn't have that authority in Azure. So they needed to go back to their Azure people and say, can you give me a service principal that has the authority to do this? So that's just a trap to watch out for, that you may not actually have the service principal that you are using may not actually have the ability to do that.
Is that stored in clear text?
They're stored as they're basically hashes. They're long keys. So, but yes, it's stored in the SIB as the full thing.
Yeah. So these aren't your Azure credentials for the portal. It's essentially it's an app, kind of like an application you create.
Yeah.
And
it's not actually a person's login and password.
Okay, thanks. Okay, so in the meantime, all right, we need to do something different for fencing. All right, we want to absolutely make sure that these services come back as quickly as possible. So we need to use a different fencing mechanism, and for that we choose SBD, all right, which stands for Shared Block Device, STONIF Block Device, Storage-Based Def. Anybody got any more? Because it's been around for forever. Everybody calls it something different. But if you just think SBD, essentially all it is, it's a shared disk which all the nodes in the cluster can see. Now, I've mentioned already, right now, most public cloud providers don't provide a shared block device, so we need to find a different way to provision that. So what we're actually doing is using iSCSI to provision that raw block device, because then when that turns up inside the nodes inside Azure, they can't tell the difference between something provisioned via iSCSI and something which is based off a SAN or anything like that, all right? So once we have delivered at least one shared disk, potentially up to 3 shared disks into that cluster, we can then use SBD as a fencing mechanism. We no longer need that ARM resource agent we've been talking about so far. And suddenly your fencing time goes from 2, 3, 4, 5, 6, 10 minutes down to potentially seconds. As soon as the cluster realizes it's failed, we'll initiate a fence. And it does that by instigating a kernel panic into the other node of the cluster. Got anything more to say?
So stun a block device is our generally recommended. By generally, I mean everywhere, because this was one of its design goals. It was designed to be independent of hardware, independent of any particular hardware or platform. It's our generally recommended fencing device. It's highly reliable thanks to hardware watchdog integration. I'm not going to go into, as Stephen knows, I can talk about this stuff for literally hours. Yeah. There are some really cool guys down in the solutions lab who will be happy to explain all this stuff to you. Why we make this claim and why we're justified in making this claim that it is in fact highly reliable. It has integration with Pacemaker and Corosync. What do I mean? You notice that's underlined. It must be important. This one. If you think about Stephen's diagram with the fencing devices, historically, when SPD was first written, loss of the SPD device was fatal, right? Because if we cannot safely fence, we can't safely be a member of the cluster. And a node that lost access to the SPD device would self-fence. That's not true anymore. Right now, loss of the SPD device is not fatal by default because of this integration. Essentially, what it means is that if you... Stephen, can you go back a slide? Thank you. If you think about this is your cluster running your actual applications. Those are the things we need to keep up, right? This is the important stuff. If an SPD device goes away, what the nodes will do is they'll look and say, okay, I can't see the fencing device anymore, but are you still there? And is everything okay? If everything is okay, we don't need the fencing device. So as long as Pacemaker and Corosync are saying that everything is healthy, these guys can come and go as they please. Okay, now bear in mind though, that if you lost the fencing devices and then these two disconnected from each other in some way, then they will both commit suicide. They have to. It's the only safe thing to do. People think, fundamentally, people think clusters are all about, oh, I need to keep my server up. No. HA doesn't care about servers. It will burn servers to keep the service alive. And so you think, oh, then the most important thing is service availability. No, the most important thing is data integrity. We will burn the services to protect the data. If you cannot guarantee safety, then the safest thing to do is commit suicide. And the nodes will do that. But the important thing, and go forward, is right now, those separate SPD devices do not represent a single point of failure to your cluster. Even if you've only one of them. If you have one of them and it dies, as long as the two cluster nodes are alive and healthy and talking to each other, everything will stay up.
Thanks. Okay, so I think we've done fencing to death at that point, so...
No.
No? So we talked about this IP address, this idea that we need a client IP address for those applications or the clients to connect into the applications that we're protecting via HA. Now, again, if this was an on-premise world and you owned everything from the network through to the infrastructure, through to everything, you would just bind up an IP address and you would potentially be able to resolve that from anywhere in your data center. It doesn't work like that when you move into the public cloud. You need to do something a little bit different. Now, in the case of Azure, what we do is we use an Azure internal load balancer to provide the front end for that IP address. So the IP address that we actually do still bind on each of those two nodes in the cluster, the fact that they're bound up as IP addresses here makes no difference at all, because anytime you're connecting to this application, you're coming in through this load balancer, and then the traffic will be routed down those particular routes depending on where the service is alive. So, do you want to talk about that?
Yep. So this is a typical Corosync representation of an IP address, telling the cluster how to manage the IP address. And in most environments, on-premises VMs or physical machines or something, that would be enough. Let's say the IP address is here. Okay? And this node fails, and it goes to there. How do the clients know it's over here now? And people say, well, the network just knows. How does it know? I mean, if you think about it in switch port terms, how does it know that that IP is not on that switch port anymore, but it's on that one? It's not at the end of that cable, but it's not the end of that one. ARP. Right. Because we ARP the thing, right? Okay, because we have a layer 2. Okay. In software-defined networks like Azure's, one way of looking at it is there kind of isn't a layer 2. So when we move the IP address that represents our service from one Azure VM to the other, that's fine. That will happily work. But the rest of the Azure world doesn't know anything about that because there's no equivalent of that ARP, that gratuitous ARP. Does that make sense? So what we have to do is we have to sort of tell it, give us a clue. And the way we do it is we run a second resource. And this resource uses this binary, user bin nc. Does anyone know what that is, nc? Netcat. Okay? We run netcat, and we run it with command line options, -l, -k, which tells it to run in the background and listen on this port. And the port can be anything. It's not the port your application uses. It's just some random number. Okay? And we tie that to this IP address in Pacemaker. The result is that on the machine that has the IP address, this port is open. Does that make sense? Now, what we then do is we go up to the Azure load balancer and we tell it, you're fronting this IP address. And the health check for the IP address is the presence of this port. So although it's a load balancer, only one leg of it is ever alive at any given moment. But it's the leg that points to the actual IP address. It's quite clever. It's quite a clever workaround, I think. So obviously, if you have multiple IP addresses, you're going to need multiple netcats running. So each IP address is now paired with a netcat that opens just some arbitrary port. There's no service backing this except the netcat. It's just some arbitrary port opened that gives a clue to the Azure load balancer which machine is currently the live one. Make sense? Yeah, good.
Thanks. Okay, so the diagrams are going to get a little messier at this point. But at the end of the day, you're protecting an application. That application is going to need some data. And for that data to be shared amongst cluster nodes, you need some shared storage. On-premise, that's easy. You would have a SAN to deliver that. In the world of Azure, you need to do potentially any number of things, but the two most popular ones we see is the first one is delivering NFS. All right. Now, as I've said already, NFS as a service doesn't yet exist. It's probably coming. All right. I want everybody here to go down to the Microsoft booth and ask them for the roadmap to see when it's coming, because it will turn up at some point. And once that happens, you don't have to worry about this. But until then, if you need NFS as shared storage, you need to go and build your own cluster. All right, so you need to provide the NFS service. And you can do that quite easily using SUSE Linux and an NFS service we provide with that. But the thing is, you then need to make that highly available as well, because then your data becomes a central point of failure. So let's make that highly available too. So how are you going to make that highly available? You're going to build another HA cluster to protect the data, as well as one protecting your application as well. Now, again, in order to make data highly available between two nodes in a cluster and have this completely synchronized, we need to fall back to some technology which has been around for 10 years and we've traditionally used on-premise for customers that didn't want to deploy SANs. So for now, in Azure, in order to build an NFS cluster, you need some SLES, you need an HA wrapper around that, and in order to synchronize the data between your two NFS nodes, you need DRBD.
So DRBD is a block device that's mirrored with a block device on one computer, mirrored with a block device on another computer. It stands for Distributed Replicated Block Device. Why are we doing this? We're doing this because we don't have a shared disk. You see, typically, if you had an on-premises NFS cluster, you would have a SAN backing or something, so you'd have actual shared block devices. In Azure, we don't have that. So what we do is we make one. And we use DRBD, which is essentially RAID 1 across IP networks. Taking a device, a block device, and it can be a real disk, it can be an LV, it can be anything, any block device, on one machine, and mirroring with with an LV or disk or whatever on the other machine over the network. So essentially, from the application's perspective, you're still coming through. You have the service running. You're coming through the Linux page cache. You're going to the file system, to the DRBD block device, and the I/O scheduler, to the disk driver, and out to the disk. But you're also branching off, going to the network stack, going out the NIC driver, and going over to the other side. So you write to both sides. Okay? This is a technology we've had around for quite a while, and it works really well. And it's interesting, it was one of those things that on premises, it was very much a niche solution. It was something that, for example, we have a customer here actually, not too far from here, in the southeast of the US, who are a retailer. And they put 450 two-node clusters into stores. This is about 8 years ago, I'd say, did this. And every one of those clusters was simply 2 off-the-shelf Lenovo desktop machines. And they simply created a boot partition, a root file system, and then an LV with the rest of the disk on both machines. And they ran it. They ran MySQL on it. Works great. It's transaction safe because it's synchronous block. It's synchronous at the block level. Okay. So DRBD is configured by a number of configuration files. Typically in the etc thing. So typically what you do is, the two things you need to know is there's this directory DRBD that contains the include files. And this file, global_common.conf, is where all the DRBD tuning goes. Now the reason I mention this is that there is a TID, or there will be a TID. I have to check the status. That will provide our recommended tuning settings for DRBD in Azure, specifically, because the defaults, yeah. So look, you can go to our support site and search. I don't know if it's available yet. Do you?
I don't think we've got it published in time for this.
Published in time for it, but it will, and that's the result of our support guys spending the last 12 months looking at customers, customer incidents opened about this. So there will be a TID. If it's not already available, that gives you a big block, and the settings, it's almost unreadable because each of the parameters is like this long, and then it equals 3. So it's kind of difficult to read. So it's a real cut and that's what I recommend the TID because it's a real cut and paste job. It's very easy to typo. And then you've got there's also files with extension .res, which actually define the DRBD devices, the blocks. And you can have more than one. You can have a machine that has 3, 4, 5 DRBD devices like mirrored with another machine. That's perfectly fine. And that's why we do it this way. Rather than define everything in a single conf file, you have independent resource definitions for each DRBD device, each mirrored pair.
Thanks. So right now, if you do implement NFS backed by, if you implement NFS backed by DRBD, then we're recommending you put that in its own separate cluster. You keep that away from your applications for the time being. The reason being is, like I say, new services get introduced in Azure all the time. So at some point, you might want to swap out NFS for an Azure-backed storage solution, in which case you could just move out or retire the NFS cluster, slide in the new services providing that file system for you, and use that instead. So that's why at the moment we're recommending to keep NFS separate away from the actual application clusters themselves. So one of the other options is to use Azure Files, which is an SMB solution which is already locally redundant and potentially geo-redundant as well, so you don't have to worry about keeping your data safe. It's an Azure service, so you're just essentially paying for the data that you're using and putting in there, and it just becomes another cluster resource. So rather than mounting an NFS file share or something like that, you're just mounting an SMB share instead, and that potentially works quite well. So
the common is this. So in future there will hopefully be an NFS equivalent to this. So why would you do that complex DRBD NRFS now rather than just do this? And in general, you wouldn't. But in specific cases, maybe you have to, because maybe that's the applications is only certified over NFS. I can think of one or two. Yeah. So so that the application vendor doesn't support the file system being mounted over SMB or whatever. Yeah. But in an ideal world, yeah. Why would you go to the trouble of setting up? Look, I'm being kind of we are open. I could say you should always run your NFS on a SUSE HA cluster because that's 2 more subscriptions for us. But no, if the service is there in the platform, use it.
Yeah, brilliant, thanks. So one last thing we kind of stumbled across because it's not that well known about, publicized or used in a lot of Azure cluster services is the Azure Events Resource Agent. So it's not, like I say, not very well documented. There is a man page if you go hunting through it, and if you really want to know what's going on, as Mark's already said, these are just scripts. You can go and have a read of them. But this is pretty cool, all right? So what this will do is it's a resource agent which sits there monitoring service metadata from Azure, and if it gets an event which says that the node that you're running on is about to be rebooted for maintenance, what it'll do is it'll put that node into standby and automatically move all your resources across to the other node. Now, that's quite cool, right? Thanks, that's a good word. But it's very clever. It's automated, which is brilliant, but it's not for everybody, all right? So if you've got a real heavy application, I know we keep talking about SAP, but a lot of the Azure clustering that we do is SAP, then you probably wouldn't necessarily use this. But if you're just protecting something a little more simpler, like a simple database, website, something like that, or another traditional application, then this could save you a lot of heartache and having to manually go in and start worrying about some of these Azure maintenance events. So well worth a look up at the man page and a read of the script if that's what floats your boat.
Can I just add something? Sorry to
Please.
interrupt you. So we just documented that a few days ago. So
Okay.
we added to the Pacemaker article, and it's also meant for SAP.
Okay.
Yes. So you can use it for SAP resources as well.
Yeah.
Sorry for.
No, absolutely right. You could use it for anything. It's a business decision as to whether you want to do that. Because, yeah. Okay.
Yeah.
Right,
As
thanks
Stephen
for that.
points out, the thing to realize though is that it will put the node into standby. Now I mentioned maintenance mode earlier. Standby is different. In standby, a node is marked, remains in the cluster. From the Corosync level, it's still communicating. But it's marked by Pacemaker as unavailable to run resources. What this means is that Pacemaker will gracefully shut down any resource that's running on it. Okay? HANA can take a long time to stop. And if it's unexpected, that might not be great. Okay, so.
Fantastic. Right. Now, here comes the exciting bit with the untested demo. Does anybody want to see this in action? The proof is in the pudding, right? So look, here I have a cluster. We are protecting a couple of nodes. So you can see at the top here we have 2 nodes online, 0 and 1. And you can see most of the resources that I have are running quite happily, I think.
Just a quick observation. If you notice, there are actually both fencing options are implemented here, both SBD and the Fence Azure ARM. And that's as documented. Now, this is a case point where I maybe go a little off message here. I do not see a situation in which Fence Azure ARM could successfully fence a node and SBD wouldn't already have killed it. Now, so by all means, it's an extra. Remember we said it takes a long time? So, and I then also claim that SBD is very reliable. So by the time Fence Azure ARM comes around to doing its thing, the node should already be dead. So this is as documented, and by all means, if you want to stay exactly to the letter of the documentation, do it. I just don't see the value. That's just my personal thing.
Okay. So I'm going to reboot node 0. and then we'll see what happens to the cluster. I'm not convinced anything will happen because I've just noticed something's not particularly perfect from the cluster resource agents. Yes?
I got a small question about that aspect of SBD. SUSE having, if you only use SBD and all your SBDs are on SUSE, what if SUSE globally have a problem, a network problem, you lose your 3 SBD, right? So like in VMware, you're going to use a shared disk, or a shared block device disk, with not SUSE, to prevent that, to have multiple SBD on different way of communicating to the SBD. But as you said, if you're like in your environment where there's only SUSE, 3 SUSE, but it's SUSE all of them, wouldn't that be the reason why you put a SUSE on the Azure protocol as well?
Potentially, yes. So, I mean, if you lost all 3 SBDs, then if everything is fine with otherwise, right, then nothing will happen because of that pacemaker integration I talked about. Loss of SBD is not fatal to the cluster. So the other instance, yes, I do see the point you're making, that if you lost all network communication.
Because in your schema, it was all on the same subnet, N0.
Right, but it could be anywhere. It's just, from SBD's perspective, SBD doesn't know anything about SUSE. They're just block devices.
Right.
So they can, in fact, best practice would be to place all the 3 SBD devices in 3 separate availability zones, or at least in an availability set. So yes, there is one scenario in which this might make sense, and that is if you entirely lost all of the networking. You could no longer reach the SUSE SBDs, and the nodes cannot talk to each other. Right? Without Defense Azure ARM agent, the nodes will.
Both shut down.
Sorry?
They will both kill themselves.
Right.
That will be to prevent that, right?
Right, but they will do that anyway. Just because you have the second fallback mechanism, SBD will kill both nodes. Again, SBD will have killed both nodes long before Defense Azure ARM returns any. So it's just a timing thing. I mean, they call this fencing topology, where you have more than one fencing agent. And in some, particularly on-premises with physical hardware, there's some interesting kind of things you can do with that. All I'm saying here is that because Defense Azure ARM is so slow, SBD will have blown the nodes away before. Now, with the new API that Stephen mentioned, then maybe there's an argument for having this as the first one.
Yeah. Or maybe you don't need SBD.
And in that, or that, I was just about to say that. In a lot of these cases with HA, it's best if you keep it simple. You try to add workarounds for more and more obscure failure cases, just makes the whole thing rickety.
True.
Yeah. And so in my view, if the API to power off the Azure VM becomes available and Defense Azure ARM is updated to do that, then I would just drop SBD. Because that would be a better mechanism, simpler. Does that make sense?
Okay, so we have 1 minute left to do the demo, wrap up, Q&A, and everything. So here we go. So the first thing is, you can see here, look, we've got our IP address here. So we've got the IP address and the Netcat service here running on node 1. So that's where most of our resources are. So what I'm going to do is reboot that. Too late. What you say? Don't what?
I said don't reboot it.
Oh, okay.
I was going to have him kill it. Because that's you see, the thing about a reboot, when you do a reboot, is it stops all the services. So what it's now actually doing is it's doing a graceful shutdown and moves everything over, which is not quite the same as a failure. In particular, there's no fence issued here. Remember I said we always fence. Well, we always fence as long if there's a problem. In this case, there's no fence. There's no fence happening.
Okay, but on the plus side, the failover started. What we'll do is we'll come back to this and see what happens. Mm-hmm. So, demo aside, do you want to cover the docs?
Yeah. So there are excellent documents documentation for this available through Microsoft, not through us. Well, obviously through us indirectly because we have some input into them. But it's if you notice, if you've been paying attention to the little links that have been going along the bottom of the screens, they're all www.microsoft.com. Microsoft has done a really excellent job of documenting all this stuff. So there's documentation for doing NetWeaver, documentation for doing all, and then there's a general document. This is the most important one, I think, for what we're talking about here. Even if you're not doing SAP, right, you just want to do HA something else, this document's well worth reading. Setting up Pacemaker on SUSE Enterprise in Azure. It covers all the stuff we've talked about here today.
Okay, thanks. So just to wrap things up, I just want to pick a couple of things out of here, namely the one at the top of the list, and that is the SUSE HA combined with the Microsoft high availability on the platform, combined with just generally how reliable all SUSE technology is, you will never ever get 100%. So if you're deploying it for customers, if you're a partner deploying it, or you are, maybe documenting it or suggesting it as an idea, just understand that you will never ever achieve 100%, because even during a failover, that service will have a blip. It will have an outage. Perhaps we'll keep that outage as small as possible. All right, that will be hopefully in a matter of minutes rather than the hours it takes to drag everybody out of bed and bring them in to fix whatever's broken. But ultimately, set the expectations correctly. We're talking about a high level of 9s rather than 100%. Is there anything you want to pick out of here at all?
Just the last line, as I just mentioned, try and keep it as simple as possible. So as it stands right now, it's maybe a little more complex than it will be in future. We have the NFS cluster, we have SBD over iSCSI. Maybe in future we will have NFS as a service. We will have Defense Azure ARM agent able to power off the nodes. In that case, the configuration will collapse pretty significantly. The amount of effort will collapse pretty significantly.
Okay, thanks. So, last thing. If you're interested in this topic, which you've sat through an hour of us, so either we've put you off for life or it's something you're thinking about doing for your business, there are a number of other workshops, case studies talking about SUSE technology on top of Azure with HA as well. So one of them's happening next door for the last hour, so you've missed that one, but there's plenty of other content on this topic that you can go and see around the rest of SUSECON. So with no time left, any questions? See what I did there? Right, okay, so look, I'm around for the next few days, as is Mark. There's a booth in the Tech Showcase which covers all of this technology and more. Please feel free to ask any questions to anybody in a black or green shirt during the week, and I hope you have a great week. So thanks very much for coming along. Cheers.
Thanks. Thank you.